Thanks for organizing this nice event and inviting me. So let me get started. So first of all, we are a group which is fairly new. So it's just me and 3 PhD students for now. And yeah, I thought about like what to talk about today. And then I decided to not to really jump into a lot of details, but to more show what is the direction that I have in mind for the group and what my general kind of interests are and what I would kind of recommend my students and ideally for some other researchers to kind of work more into with us. So to put what I exactly mean by trustworthiness in machine learning, I would like to phrase that as a transition from the focus on what to how eventually. So what I mean by what task is, let's say you have an image and the label. And if you just train with that, then there can be, for example, 2 ways of solving that problem. And I see that as a bit of problem because you're not given a direct direction guidance of what is the right way to solve the problem. For example, here there are 2 ways of solving it, using the car body or the road. Okay, and one of the cues can be a kind of causal, while the other one is non-causal and probably does not generalize very well in other situations. And I call this kind of Z variable. So you're training the whole system with XY pairs, but not with exact Z given by humans. And so the model is free to do whatever they want to do with the prediction. If it works for the XY kind of data, then they can even choose non-causal spurious cues for making the prediction. And the problem is, let's say you have those kind of data where, for example, you always have cars on road and you always have frog in swamp. Okay, then and you never see a frog in other background, for example. Then the background cues themselves can be very strong cue for making the recognition possible, right? So when the cues kind of change later on, then you do not succeed in recognizing those samples. For example, by seeing the swamp cues here, the model's prediction can be just frog here, and so on. So that's part of the problem of not giving the right guidance on how the model should be solving the problem. So in short, whether you have solved the problem, it seems, is not enough at the moment. And now how you actually solve it matters a lot. And that also has to do with the robustness and explainability of AI systems. Okay. So that leads to a bit of observations on the trustworthiness aspect. Can you trust the models now, right? To give you a more precise or more visualizable examples of whether you can actually trust the current systems or not, I can give you 3 examples here. One is driverless car. For example, can you actually take your hands off when your driverless car is driving along a cliff, right? And for medical decisions, can you actually delegate all the decisions to machine learning models yet? I guess not. For financial investments as well, let's say you put 1 million in your account, and the question is, can you actually go to bed? I guess not. It's quite hard. So these are some of the research directions we have in mind for the group at University of Tübingen. So there are 3 pillars. One is robustness. That is to say, the models must work well beyond the training set. So it should generalize well. There can be different aspects of generalizing well beyond the training set. For example, like when people say robustness, that usually means robustness against some adversary as well. But here, what I mean is even for natural changes in distributions, the model should be ideally ready for the changes that it's going to see in deployment time. The other aspect is explainability, which is the focus of this workshop. So models must explain in themselves the why and how questions. And I think uncertainty is also very much related to the topic of explainability, because that also explains the model's own uncertainty and confidence about their decisions. And now we are actually seeing quite some shift of focus of machine learning towards those how questions. So that is happening a lot in computer vision as well, because now we do not only have one type of evaluation benchmark for image classification task. For the same benchmark, that is to say ImageNet, you're seeing different variations of test sets, like what happens if you add more noise or some natural possibilities that could happen at test time to make your prediction go wrong. Or there are some corner cases where the models are probably not ready for because the training set does not contain enough of them. Or it's kind of more synthetic and adversarial kind of case where you erase some of the cues from the image and still try to see if the model is performing all right. Or you can kind of combine different cues from different images and still try to see if the model is doing the correct job. And for natural language processing as well, now people are not happy with just an answer, but you wish the model to kind of give an reasoning towards the final answer, for example. So like for this kind of math question, the model should output the chain of thought leading to the final answer. And they also say it helps also to make the final answer more correct. So this is a nice example of seeing the synergy of explainability and the actual improvement in practice. So so these are the current status of how people are approaching this explainability and trustworthiness problem in general. I would like to first conceptualize how this is done, and I would like to talk about how we are kind of approaching it. So there's input and eventually you want an output. But here, now we started to care about the Z aspect, the how aspect of cues, explanations, reasoning, and so on. So I can say machine learning 1.0 was about learning the relationship between X and Y. But now, in the second generation, we are caring about X, Y, and Z together. But if you look at how this is trained, we find in many cases that you're actually training the X, Z, and Y, or you care about X, Z, and Y. But for training such a system, we're just giving X and Y pairs. Partly because for most of the data sets, we do not have the how aspect recorded from humans. And so we are kind of bound to whatever ingredients we already have from humans. And therefore, naturally, it makes sense to just use X, Y data to learn X, Z, and Y. Okay. But the question is this really possible? So I give you an example to show that this is not possible conceptually. So I have such a toyish data set of circle, triangle, and square, and label them 1, 2, 3. Okay. So if you look closely, actually, there are 3 variables or 3 features that are changing: the size, the color, and the shape. Okay. So actually, if you see a completely new combination of those 3 cues at test time, the prediction can actually be all 3 of them, right? 1 makes sense based on the scale of the size of the shape, and 2 also makes sense in terms of the shape, and 3 makes sense in terms of color. Okay, so it actually depends just on the cue that is used for recognition. And therefore, if you're just giving the X and Y pairs for training such a system, then you cannot expect the model to follow what you have in mind as the right cue. Okay, so this is inherently ill-posed problem with respect to arbitrary choice of the pathway. So I'd like to kind of picture the status quo of approaching the how problem, the Z problem, using X and Y data. And I expect there to be a little bit more improvement using the same ingredients like this. But what I'm saying is probably using the ground truth X, Y, and Z data, we have actually a lot more to achieve later on. So, but then the next question is how do you collect X, Y, and Z data? Because they're often quite expensive. So the research question here is, rather than to increase the upper bound using X and Y data only, it's sort of dual problem because we are trying to kind of achieve the best score while relaxing the constraint of given by the data itself. What is the minimal cost solution for collecting such a data, which is going to give me the full solution of the problem? So these are a summary of some of the directions that we're looking into. So one direction is actually better understanding what humans are actually doing for making recognition possible, because in that process, we expect a lot of cues to be there. So for example, we're thinking of collecting sketches data because, yeah, there was also an example of quick draw from 2 talks ago, and there you see a lot of simplifications. If you compare the real images to those simplified images, you're going to see a lot of abstraction and a lot of more kind of focused strokes, more efficient. And that shows us a lot of hint of how humans are actually simplifying and symbolizing stuff in the real world. And we hope that such data can also give the models further cues of how they should actually align with humans' way of recognition. And probably that's gonna give us more robustness and better generalizability and better explainability that's more aligned with the human's way of understanding in the future. And the second approach is, of course, try to collect more how signals from humans themselves in a cheap way. We're actually missing a lot of peripheral signals from annotation procedure. For example, there are some work on recording where people are looking at when they annotate images. And actually, there was a recent project that we did where we tried to record the mouse traces and the click locations when they do ImageNet annotation task. And we internally showed it improves the generalizability quite a bit, and also the explainability measures, the robustness measures. You can also let people just write down in natural language why they think the label was so, and that's gonna give us the direct Z label. And of course, we have nice language models these days, so these are understandable by machine models. There's also work on this is OpenImages localized narratives. I really love this data set, but I don't see actually a lot of people using this data set yet. It's fairly old as well, 2 years. And this is the data set of captions. But when people are, when the annotators are describing the image through voice captions, they also point to the object, the corresponding objects in the image. And that mouse trace is kind of registered with the voice, and then the voice is transcribed. Okay, so this is a very rich data set with a lot of hints of what they actually mean by each word and so on. So this is a nice ground truth, I believe, for training the X, Y, Z system. Okay, and then there's a third aspect, which is the evaluation. if you try to evaluate such a system, it becomes super hard because this is an instance of utilise task because you're trying to learn XYZ relations from just XY data, from a bit of human guidance. That's what a lot of people are doing these days. And solving this is ill-posed in general. And the trouble comes in when you try to benchmark it and try to make it a fair comparison against the others. And there, you're going to see a lot of hidden ways where unallowed, prohibited ingredients come into the playground. And I mean, this is encouraged over and over time because you need to kind of beat the others throughout time. And this is easily possible by including more prohibited ingredients into the system. And about this, we actually have one tutorial from ISSV 2020. So if you're interested, you can also take a look at that. Oops. Yeah, I'm not going to play that. And then I'm also interested in mathematical ways of solving the how problem, because if you look into mathematics, there are a lot of tools for ground up systems, such as dynamical systems, a system of ODEs, which is including a lot of human intuition of how the system should be working. And if you combine those systems with data-driven learning, then I'd presume there's a lot of room for improvement for the current systems. So, yeah. And the 5-year research aim eventually is to make a quantum jump in productivity, which I believe is the goal of machine learning at this stage. And this is what Sundar Pichai said, advances in AI will be more profound than electricity. But I think, to be honest, the biggest hurdle from here to there is really the trustworthiness of machine learning systems. So I'm really trying to solve this problem in 5 years. That's it, and I hope to get questions.